Hello everyone. Welcome everyone to the discussion of work, energy and power. NCERT question discussion of work, energy and power. So let's start with the first question. In the first question we have the sign of work done by force on a body is important to understand. The sign of work done by a force on a body is important to understand. State carefully if the following quantities are positive or negative. So we know that sign of work done is very important in the study. So we have to in this exercise we have been given 5 different scenarios, and we have to tell whether the work done is positive or negative in all these scenarios. So the first question is work done by a man in lifting a bucket out of a well by means of rope tied to the bucket. So here work and the question is asking about the work done by a man in lifting the bucket out of the well. It means when the man is applying force in order to lift the bucket, then the motion is in the direction of the force applied. So of course when the motion is in the direction of force applied, then the work done by that force is going to be positive. And the second scenario is that work done by gravitational force in the above case. So when the bucket is being lifted out of the well, the displacement is in the opposite direction of that of the gravitational force, so the work done by gravitational force is going to be negative. And the third scenario, we have work done by friction on the body sliding down the inclined plane. So friction force opposes the motion of the body, so it is always going to be negative. Now in fourth case, we have work done by an applied force in body moving on a rough horizontal plane with uniform velocity. So if the body is moving in a uniform velocity on a rough horizontal plane, then the man is applying the force which is used to resist the frictional force due to the rough surface, so the work done by the man is going to be positive. And in the fifth option, we have work done by a resistive force of air on vibrating pendulum in bringing it to rest. So frictional force here is opposing the motion. So when the force opposes the motion, the work done due to that force is negative. Let's go to the next question. In this question, we have been given that a body of mass 2 kg initially at rest moves under action of applied horizontal force of 7 Newton on the table with coefficient of friction 0.1. Compute the work done by the applied force in 10 seconds. So we have to find out work done by applied force in 10 seconds. We know the formula for work done is the component of force along the displacement times the displacement, or we can say that on the vector notation it is F dot D, which is the dot product, so F cos theta D. Now in the first scenario, we see that work done by the applied force in 10 seconds. So whatever the motion, whatever the displacement will be in 10 seconds, that would be the displacement by that force. And since it is given that a mass of 2 kg is initially moving at rest, applied horizontal force of 7 Newton with the kinetic of friction, with the coefficient of kinetic friction as this. So here we will simply multiply the force with the displacement in 10 seconds. We will get the value of work done. And work done by the friction in 10 seconds. So friction would be opposing the motion. So the work done by friction is opposite, is in the opposite direction by the of motion. So it would be equal to the displacement times the frictional force, and frictional force is given by mu, that is 0.1 times normal reaction or the weight of the body. So normal reaction would be 20 Newton. So 20 times 0.1, or so 2 times 9.8 times 0.1 would be 1.96 Newton. So this would be the work done by the frictional force. And the third question, we have work done by the net force on the body in 10 seconds. So net force would be the applied force minus the friction force. So it would be something like this, 5.04 times the displacement. And now the fourth option is check change in kinetic energy of the body in 10 seconds. So initially the body was at rest, and since the body is moving with some motion, so we can also apply here the work energy theorem, which says that net work done by all the forces is equal to change in kinetic energy, and work done by all the forces include the net work done by the applied force, that would be equal to 882 minus 246 joule, and that would be equal to 635.04 joule. Let's go to the next question. So in this question we have given that 5.11 are example of some potential energy functions in one dimension. The total energy of the particle is indicated by a cross on the ordinate axis. Ordinate axis is the y-axis. In each case, specify the reason in A, if any, in which the particle cannot be found for any given energy. Also indicate the minimum total energy of the particle must have in each case. Think of the simple physical context for these potential energy function shapes are relevant. So here we have to find out in which of the regions the particle cannot be found. So we know that total energy is equals to kinetic energy plus potential energy, and total energy can never be the energy of body at any moment can never be greater than the total energy. So here we haven't given that the total energy of the particle is indicated by a cross on the ordinate axis. So E is the total energy in all those 4 diagrams. So in the first diagram we see that the particle after x equal to A position, the particle has gone the position, the energy of the particle is higher than that of the total energy. So this zone is completely impossible. So the particle is going to be here, that is from from 0 to A, or from negative of the x-axis to A. Now in the second question we have again in the whole plot we see that the total energy of the particle is higher than that of the total energy given. So this whole figure is not possible. Now in this next question we have, now here we see that from the particle from x equals to minus b by 2 from the left direction of the x-axis to minus b by 2, the total energy of the particle is less than the E, that is given by the cross on the ordinate axis. So the particle is available in that zone, and in this zone the particle is not available because the total energy has gone higher than that of the specified level. So so this zone is not possible. And now again we see the symmetrical behavior over here, that after x equals to b by 2, the particle can be found in the physical state, except from A by 2 to B by 2, because the energy level of the particle from A by 2 to B by 2 is higher than that of the total energy specified, that is E. So the particle can't be found. Now in next question we see again we will apply the same theory, that the total energy of the particle can't be greater than E. Now now if we plot the horizontal line on the E point or the cross point, we see that from x equals to minus infinity to A, the energy is higher than the total specified energy. So this is not physically possible. And from x equals to B to beyond, again the energy is higher than that of the specified total energy. So it is not physically possible. Let's move to the next question. So in this question we have been given that the potential energy of a particle executing linear simple harmonic motion is given by V equals to kx square by 2, where k is the force constant of the oscillator. For k is equals to 0.5 Newton per meter, the graph of Vx versus x is shown in figure 5.1 to show that a particle of total energy 1 joule moving under this potential energy must turn back when it reaches x equals to plus minus 2 meters. So conservative force can be given by negative derivative of potential energy, negative with respect to the distance. So as per the given question, the potential energy function is given as kx square by 2, So the force would be equal to minus kx, which happens to be the spring force, and it is conservative in nature. So the total mechanical energy of the system is conserved if the forces doing work on it are conservative. So in this case also we see that total energy would be conserved because the spring force is a conservative force. Now we have to show that the total energy of the particle is 1 joule. So what it is saying that the potential, we have to show that the particle with the total energy of 1 joule moving under the potential must turn back when it reaches x equals to plus minus 2. So the potential energy, we will find the total energy of the particle here. So it would be equal to kinetic energy plus potential energy. Now the reason, that is the point at x equals to plus or minus 2 is the point where the particle is going to be having maximum potential energy, or we can say the total energy will be composed of only potential energy. Now that potential energy can't exceed the total energy level, so the particle must convert it into the kinetic energy for this theory to be true. That is, the total energy can't be greater than the kinetic energy plus potential energy. So we see here that after the particle has reached this position x equals to 2 meter, it must decrease and the kinetic energy will increase, because this is the case of simple harmonic motion, and the simple harmonic motion that we will read in the next chapters, the potential energy is maximum at the extreme position, and after that the potential energy is converted into kinetic energy as the particle moves towards the mean position. Let's move to the next question. The casing of a rocket in flight burns up due to friction. At whose expense is the heat energy required for burning obtained? So as the rocket moves through the atmosphere, friction between the rocket surface and the air molecules generates heat. Now this frictional force acts against the rocket's motion and converts kinetic energy into thermal energy. So the source of energy here would be the kinetic energy of the rocket is derived from its motion, which in turn comes from the energy of the fuel. And as the rocket moves, some of its kinetic energy is transferred to the air as thermal energy, which causes the casing to heat up and eventually burn. Now the B question is, comets move around the sun in highly elliptical orbits. The gravitational force on the comet due to sun is not normal to the comet's velocity in general, yet the work done by gravitational force over each complete orbit is 0. Why? So gravitational force is conservative in nature, and it is not a path function, it is a point function. So on a complete circle its work is going to be 0. The work done by gravitational force over a complete orbit is 0, because the gravitational force is conservative in nature, and net work done by conservative force over a closed path is always 0. Now the third question is, an artificial satellite orbiting the Earth in a very thin atmosphere loses its energy due to gradual dissipation against atmospheric resistance, however small. Why does then its speed increase progressively as it comes closer and closer to Earth? So the speed of the satellite increases as it comes closer to the Earth because the gravitational pull becomes stronger, and in lower orbits the satellite must move faster to maintain its orbit. The increase in speed compensates for the loss of altitude, even though the satellite is losing energy due to the atmospheric drag. Now in fourth question, we see that a man, in figure 5.13, a man walks 2 meters carrying the mass of 15 kg on its hand, and in the second figure we see that he walks with the same distance pulling the rope behind him. The rope goes over the pulley and the mass of 15 kg hangs on its other hand. In which case is the work done greater? So the work done is greater in the second case over here, because in the first case the force exerted is vertical while the displacement is horizontal, leading to the no work done in the direction of the force. In the second case, the force and displacement are in the same direction and resulting in the positive work done. So here force is acted upon by tension in the string, which is in the same direction of motion of the man. So the work done by this in the second diagram is higher. Let's move to the next question if you don't have any doubts. So the question says that when a conservative force does positive work on the body, the potential energy of the body increases or decreases or remains unaltered. So when a conservative force such as gravity does positive work, when it moves an object in the direction of the force, the potential energy of the body will decrease because the height of the body will decrease. The second question is, work done by a body against friction always results in a loss of its kinetic or potential energy. So friction force is a non-conservative force that opposes the motion. When work is done against the friction, it typically converts kinetic energy into thermal energy, resulting in the loss of kinetic energy. So it would be kinetic energy. Now the third question is, the rate of change of total momentum of many particle system is proportional to the external force, sum of the internal force of the system. So according to the Newton's second law, the rate of change of the total momentum of the system is equal to the net external force on the system. So it would be external force. Now in the fourth question, we have in an inelastic collision of two bodies, the quantities which do not change after the collision are the total kinetic energy or the total linear momentum or the total energy of the system of the two bodies. So in an inelastic system, the kinetic energy is not conserved, but the total linear momentum and total energy is conserved. So the correct answer would be total linear momentum. Also, the total energy of the two bodies will be conserved. Let's move to the next question. So it states that, state if each of the following statement is true or false. Give reason for your answer. In an inelastic collision of the two bodies, the momentum and energy of the body is conserved. So in an elastic collision, the total momentum and the total kinetic energy of the system are conserved. However, the momentum and kinetic energy of each individual body are not necessarily conserved. So it is going to be false. Now the second question is, total energy of the system is always conserved no matter what internal and external forces on the body are present. This is false because the total energy of the system includes all form of energy, kinetic, potential and thermal. According to the laws of conservation of energy, total energy in a closed system is conserved. However, if external forces like friction act on the system, they can do work on the system, converting one form of energy to another. So when external force is present, it is not going to be conserved. So it is false. Now this next question is, work done in a motion of a body over a closed loop is zero for every force in nature. This is only true for conservative force, so it is not true for every force in nature, so it is going to be false. Now in fourth question, in an inelastic collision, the final kinetic energy is always less than the initial kinetic energy of the system. It is generally true, but not always true, because we can have certain collisions where final kinetic energy becomes higher, like in the nuclear fission reaction, it becomes higher. So it is not always true. Now in this question, we have, in an inelastic collision of two billiard balls, is the total kinetic energy conserved during the short time of collision? So during the short term of so the question is asking that in an elastic collision of two billiard balls, is the total kinetic energy conserved during the short time? So actually it is not conserved. Why? In an elastic collision, while the total kinetic energy of the system is conserved before and after the collision, During the actual contact between the balls, some of the kinetic energy is temporarily converted into potential energy due to the deformation of the balls. That's why it is not conserved. Now in the second question we have, is the total linear momentum conserved during the short time of in an elastic collision of the two balls? So yes, the total linear momentum is conserved during the short term of the collision. Now the third question is, what are the answers to A and B for inelastic collision? So kinetic energy will not be conserved. The total kinetic energy is not conserved during the short term of the collision in an inelastic collision because it is converted into the heat or sound or other forms of energy, and linear momentum is conserved. Now the fourth question is, if the potential energy of two billiard balls depend only on the separation distance between their centers, is the collision elastic or inelastic? So if the potential energy of the billiard balls only depends upon the separation between their centers, then it is going to be elastic in nature. If you have any doubts, you can ask right now. So I'm taking a pause for 5 minutes, then we will proceed to the next question. So the question says that the body is initially at rest. It undergoes one-dimensional motion with constant acceleration. The power delivered to it at time t is proportional to. We have been given 4 options where the order of t is varied. Now we know that work done is defined as mass times force is defined as mass times acceleration, and work done is defined as force, the dot product of displacement and force, and the power is defined as the derivative of time, work done with respect to time. Now if we find the expression for work done with respect to time, then displacement has displacement has order of time of 2, and when we take the derivative of work done, then we will find that work done is, and power is proportional to t, or this, or it varies linearly with time. So we can say that the power is proportional to t raised to the power 1. Now in next question we have, a body is moving unidirectionally under the influence of source of constant power. Its displacement in time t is proportional to what? Now we know that kinetic energy is given by half mv square. Now it is given over there over here that the power is constant, so the derivative of this kinetic energy is going to be constant with respect to time. We here find the derivative of kinetic energy, and we get that mv dv by dt equals to k, that is constant. Now if we have been asked that its displacement in time t is proportional to. Now in order to find the displacement, we will integrate the velocity with respect to time to get the displacement. Now we find that displacement is something that is constant times t raised to the power 3 by 2. So it is proportional to t raised to the power 3 by 2. Now the next question is, a force constrained to move along the z-axis of a coordinate system is subjected to a constant force F given by F equals to minus I cap plus 2j cap plus 3k cap Newton, where I, j, k are the unit vectors along the x, y, z axis of the system respectively. What is the work done by force in moving the body a distance of 4 meter along z axis? Now work done is defined in a vector form as F dot d, that is the dot product of force and displacement. So here the displacement is only in the z-axis direction, that is in the k cap direction, k cap unit vector direction. So if we take the dot product of it, we will get the solution. Now the next question is, an electron and proton are detected in a cosmic ray experiment, the first with a kinetic energy of 10 kilo electron volt and the second with a kinetic energy of 100 kilo electron volt. Which is faster, the electron or the protons? So we know the expression for kinetic energy, that is half mv square. Now here we have been given mass of electron and proton, that is me and mp. Now we know that the ratio of this kinetic energy and ratio of this electron and proton has been given. So we will divide the expression with the given ratio, and we find out that velocity of electron is 13.5 times that of the proton. That is, electron is 13.5 times that of the proton. Does it matter if it is minus k or plus k direction? So I think he is asking about the previous question. If we take the dot product, we know the formula for dot product, that is dot product is essentially the the expression for dot product is f cos theta d. So cos theta d, when you are talking about minus and when you are talking about the minus and plus directions of unit vector, then it is plus k cap is in the positive direction of the z axis and minus k cap is in the negative direction of z axis. So obviously the work done will differ by its sign, that is, if it is plus k 4k cap, then it is going to be 12 joule as we see here, and if it is minus 4k cap, then it is going to be minus 12 joule. So the work would be negative if it is minus k cap. So kinetic energy is the energy possessed by a body by the virtue of its motion. So whenever any body that is having mass, it is moving with certain velocity, certain speed, then it is the energy that is having by the virtue of its motion is the kinetic energy. By the virtue of its motion, meaning to say that the body that and the energy that is in the body, because there is motion in the body, then that energy is going to be called as kinetic energy. Let's move to the next question. Now question here is, a raindrop of radius 2 mm falls from the height of 500 meter above the ground. It falls with decreasing acceleration due to viscous resistance of air until half of its original height. It attains its maximum terminal speed and moves with uniform speed thereafter. What is the work done by gravitational force in the drop in the first and the second half of its journey? What is the total work done by resistive force in the entire journey if its speed on reaching the ground is 10 meter per second? So here we have to find out work done by the gravitational force and also by the frictional force. And the journey is like in half of the journey, the body was accelerating, the raindrop was accelerating downwards. But in the entire journey, the gravitational force acting on the body is going to be same. So the distance traveled. And also we have been given that the terminal velocity, that is the velocity of the raindrop on reaching the ground, is 10 meter per second. So we have to find out the work done by gravitational force and the frictional force in the first and second half of the journey. So work done by gravitational force in the half of the journey is going to be mgh, and we can find out the height. We haven't given the height of 500 meter as the total height, so the half of the height would be 250 meter. So when we use this formula mgh, then we will get the work done by gravitational force, and because the raindrop is falling in the direction of gravitational force, then it is going to be positive. Now similarly, the other half of the work done by gravitational force will be the same as it is conservative force, and work done is a state function. So as I said earlier, the gravitational force acting on the raindrop will not change. So work done by gravitational force is going to be equal to the total displacement, that is 500 meter, times the force that is applied on the raindrop, and the force would be equal to mass of the raindrop. We haven't given the radius, so we can easily find out the volume, and when we will multiply it with 1000, then we will get the mass of the raindrop in kg. So we will get the work done by gravitational force, and again total work done by frictional force can be found out using the work energy theorem. So work energy theorem says that total work done by all the forces is equal to change in kinetic energy. Why should we take the center of mass of the body? What is COM of body as displacement? So COM, if it is center of mass, then center of mass is an assumed position where we assume that the mass of the body is acting at the center of at that point. So if we assume that any body is a particle, then it is very much convenient for us to take the center of mass concept, because then we can assume the whole body as a particle, and that particle of mass, given mass, is just concentrated at center of mass. So the assumption of a body as a particle becomes very convenient if we take the concept of center of mass into account. That is why it is always advisable to work with the center of mass concept, because if we take the structure of the body into account, then we have to take the geometry also, which is not the scope of this level of physics. So that's why the concept of center of mass is required to idealize any body as a particle. Let's move to the next question. A molecule in a gas container hits a horizontal wall with a speed of 200 meter per second. So is your doubt clear, Savita R? A molecule in a gas container hits a horizontal wall with speed 200 meter per second and angle 30 degree with the normal, and rebounds with the same speed. Is the momentum conserved in the collision? Is the collision elastic or inelastic? So the taking molecule and wall as a system, the total momentum is going to be conserved because there is no any external force acting on the system. Now the initial and final speed of the momentum won't change as the rebound speed of the wall is 0, so kinetic energy of the system is going to be conserved, thus the collision is elastic here. A pump on the ground floor of a building can pump water to fill the tank of 30 meter cube in 15 minutes. If the tank is 40 meter above the ground, the efficiency of pump is 30%. How much electric power is consumed by the pump? So here we have to find out how much electric power is consumed by the pump, given the pump is having 30% efficiency. Now power, we know that the work delivered per unit time is known as power. Now we can easily find out the work done by the pump, because the tank is 40 meter off the ground, so we can, using this expression of mgh, we can find out total potential energy that 30 meter cube of water will be gaining, and in what time we know, that is 15 minutes. So we can easily find out the work done, and the time is also given. So work done per unit time is known as power, and when we will divide it by 0.3, then we will get the exact power that is consumed, 43.55 kilowatt. I will take a pause for 5 minutes and then I will be back. The question says that two identical ball bearing in contact with each other and resting on the frictionless table are hit head on by another ball bearing of the same mass moving initially with a speed v. If the collision is elastic, which of the following is possibly the result of after collision? So we know that for elastic collision, there are two conditions that must be fulfilled. That is, the initial kinetic energy must be equal to final kinetic energy, and total linear momentum must be conserved. So in all these three cases, we see that only in case 2, the initial kinetic energy, that is half mv square, is conserved, because initial kinetic energy in the initial state only ball 1 was moving, and in the final state only one ball is moving. So we can say that in only the second case the kinetic energy conservation is being followed. So the second case is the plausible case. Now in next question we see that a bob of pendulum released from 30 degree in the vertical hits another bob of mass m at the rest of the table, showing the figure. How high does ball A rise after collision? So, and if the collision is elastic, we know that there are the two conditions must be fulfilled, that is initial kinetic energy must be equal to final kinetic energy, and initial total linear momentum must be conserved. So when it is elastic collision, then the initial kinetic energy whatever the ball A would be having will be transferred to ball B, and the ball transfers its momentum to ball B without any rise in ball A. A bob of pendulum is released from a horizontal position. If the length of the pendulum is 1.5 meter, what is the speed at which bob arrive at the lowermost position, given that it dissipates 5% of its initial energy against air resistance? So when these kind of unknown forces and non-conservative forces acts, it is better to use work energy theorem, which says that total work done by all the forces is change in kinetic energy. We know that the height of the ball is equal to the length of the pendulum, that is 1.5 meter. So the change in height would be 1.5 meter, and we have to find out final speed. So kinetic energy lost we can find out. Now potential energy, the amount of potential energy that will be converted into kinetic energy is the total potential energy minus the lost energy. So we can equate it with the kinetic energy formula, that is half mv square, and we will find the velocity. If you have any doubt, you can ask in any question, irrespective of whichever question I am in. A trolley of mass 300 kg carrying a sandbag of 25 kg is moving uniformly with a speed of 27 km per hour on a frictionless track. After a while, the sand starts leaking out of a hole on the floor of a trolley at the rate of 0.05 kg. What is the speed of the trolley after the entire sandbag is empty? So here no external forces are acting on the system. If we take the system of trolley and the sand, so assuming that trolley and sand to be the system of under consideration, no net external force is acting on the system, so the truck won't change its speed. Also, if the sand is falling, then it would continue with the same speed. So the speed of the truck is not going to change. Let's move to next question. A body of mass 0.5 kg travels in a straight line with velocity of a x to the power 3 by 2, where a is 5 per meter per second. What is the work done by the net force during its displacement from x equals to 0 to x equals to 2? We have been given the velocity. We can easily find out the acceleration, and when we derive it with respect to time, and then we have been given we have to find out the net work done. So we know that after we will get the value of acceleration, we can multiply it with the mass, then we will get the magnitude of force, and then we can integrate it from displacement x0 to 2 meter, so we will get the work done. Let's move to the next question. So in this question, we have been given that a blade of windmill sweeps out a circle of area A. If the wind flows at a velocity v perpendicular to the circle, what is the mass of the air passing through the time t? So if the radius is given, if the wind flows with the velocity v perpendicular to the circle, so v velocity has been given. Now in order to find out mass of the air passing through the windmill, we must know the volumetric flow rate, and then we can multiply it with density of the air, so we can get the mass flow rate. So in order to get the volumetric flow rate, we must know the surface area of this windmill, and then we will multiply it with the velocity, because surface area times velocity would be equal to meter cube per unit time. So we will get the volumetric flow rate, and then we can multiply it with density, so we will get the mass flow rate. Now the second question is kinetic energy of the air. Now since it is given the velocity, so we can, and also we know the mass. Now mass half times mass times velocity square would be equal to kinetic energy. Assuming that the windmill converts 25% of the wind energy into electrical energy, and that A and V is given, area of the area that the wings of the windmill sweeps, and velocity is also given, and density is also given. What is the electrical power produced? So the windmill actually converts kinetic energy of air into electrical energy. So it is given that it is having efficiency of 25%, which means that whatever kinetic energy that is being converted, 0.25 times of it is going to be converted into electrical energy. So if we find out the kinetic energy, then we will multiply it with 0.25, then we will get the value of electrical energy produced. Now let's move to the next question. A person trying to lose weight lifts a mass of 10 kg, lifts a 10 kg mass 1000 times to a height of 0.5 times each. Assume the potential energy lost in each time he lowers the mass is dissipated. How much work does he does against the gravitational force? FAT supplies 3.8 into 10 to the power 7 joule of energy per kilogram, which is converted into mechanical energy with efficiency of 20% rate. How much fat will the dieter use up? So here potential energy, when the lifter is lifting the weight, she is using the energy which is indeed coming from the fat, so that will cause the fat to burn. Now the efficiency has been given here, so we have to find out how much at first we have to find out how much work she does against the gravitational force. So if we find out how much work she does once she lifts the weight, and then we will multiply it with 1000 times, so we will get the how much work she does against the gravity. Now that work was delivered by the fat burning. Now that fat is burning with 20% efficiency, so per kg of the fat burning, per kg of the fat gives 3.8 times 10 to the power 7 joule of energy. Now 20% of it would be equal to 7.6 into 10 to the power 6 joule. So we can now calculate easily that weight of the fat used based upon the work, the potential energy dissipated. Let's move to the next question. So here it is given that a family uses 8 kilowatt of power. Direct solar energy is incident on the horizontal surface at an average of 200 watts per square meter. If 20% of this energy can be converted into electrical energy, how large an area is needed to supply 8,000 watts? Compare this area to that of the roof of the typical house. So it is given the efficiency of the solar panel, that is 20%. Now output power is 20% of the 20% of the 200 watts that is received on the surface per square meter. So the input power is, if 200 watts, then the power that we are going to use, that we are able to use, is 40 watt. Now given that 8,000 watt is the required power for a family, then when we divide it with the unit usable unit per square unit, how much power we can use, it would be equal to 40. Then we will divide it with 40, then we will get the area required, that is of 200 meters square. Now for 200 meters square, generally the area, if we assume it as a square roof, then it will take 14.14 meter of the dimension for this power to be generated, 8,000 watts. If you have any doubt, you can ask. Efficiency and power, they both are efficiency is characteristic of the machine, which means that whatever input that you are giving, how much of that input is coming out as an useful energy. Like uh, if you are giving 10 watts of electricity to a motor, then how much power of the desired work the machine is doing. Like if you are giving 100 watts and it is doing a work of 20 watts, then the efficiency of it would be 20 watts. Now let us relate it with the physical situation over here. So let us assume that there is a motor which is very much capable of lifting water to a certain height. Let us say that the height is uh, 10 meter, and 1 kg of water, upon taking it to a height of 100 upon taking it to a height of, let's say, 2 meter, we will use the energy of 20 joule, right? 1 kg water, 1 kg, and so the weight of the water would be equal to 10 newton, and when it is raising its height to 2 meter, the energy lost is it would be equal to 20 joule. Now when you are giving it 100 watt of power and it is raising the water to a height of 2 meter, then it is only using that much of 20 joule. It is delivering you 20 joule only, 20 joule of usable work done per unit time. So per unit time you are giving it 100 joule and it is doing a work of 20 joule. So that is known as efficiency. So for you it is only doing a work of 20 joule every time you are giving it 100 joule. So that is known as efficiency. And efficiency, this is efficiency in the terms of power. Efficiency can also be used in the terms of other quantities as well, like what is the efficiency of any machine to do the work. So it is a very general term, but in the case of power, I've just explained you. I hope this has solved your doubt. Thank you for today's session. We will meet soon.